Alright, so this is going to be our first lesson in the quadratics unit. Now before you've done this, hopefully you've done the investigation that I gave you guys in class that sort of had you graph a bunch of different parabolas on Desmos and try and pick out some of their key features. If you haven't done that, please make sure you do that first before you go any further, because you're going to need that for this to make a lot of sense. So please make sure you do that. Also, what I'd like you to do is create some tables of values for each of these equations. So to remind yourself how to create a table of values here, there's 4 different equations here I want you to do it with. So for example, for the first one here, y equals 3x minus 4, I'm giving you some x values here. So we have x equals negative 3. When x equals negative 3, you're going to put that value in the equation for x. So you're going to have 3 times negative 3, which is negative 9, minus 4 to give me 13. So when x equals negative 3, y equals negative 13. I want you to repeat that process for all the values for x in this table to create a table of values here, and do that with all the other equations as well. One thing I will mention here, because it's a very common mistake that happens, here when you have y equals x squared, let's say you put in the x equals negative 3, that's going to be y equals negative 3 all squared. So notice here that the negative is in brackets, so when you square it, it's the same thing as having negative 3 times negative 3, so it's actually going to be positive 9, not negative 9. Okay, so be careful because some calculators can lead you astray. That calculators won't put brackets on for you. So you're just going to be very, very careful about that. Make sure you're using brackets on your calculator. Okay, so when you're finished doing that investigation and the table of values, come back here and we'll talk about them. Okay, so take a minute here and check your tables of values. So we've got these for 3x minus 4 and y equals x squared. And then down here we've got y equals negative x squared plus 2x plus 3, and y equals 2x squared plus 16x plus 30. Now, you may have already plotted these points to get an idea what the shape looks like, and that's great. We're going to do that very, very soon. What I'd like you to do now is, you may remember doing this in grade 9, is finding the first differences for each of these equations. Now, to remind yourself of how to find these, the first difference is if you have your x values in order here in the table, you are subtracting consecutive y values to figure out the pattern. So as x changes, what's happening to y. So here you go negative 10 minus negative 13. Okay, so you simplify that, and that should give you a value of 3. Okay, here we have negative 7 minus negative 10 to give me 3 as well, and so on and so forth. Negative 4 minus negative 7 gives me 3, 3, 3, and 3. Okay, so that does it for y equals 3x minus 4. Now you may notice here that all of the first differences are the same, and one of the things you looked at back in grade 9 is if this was the case, so if you had x going up by a consistent amount every single time, so in this case it's going up by 1 every single time, and all your first differences were the same, then this told you that the equation was in fact linear. And you should recognize y equals 3x minus 4 as a linear equation from grade 9 with a slope of 3 and a y-intercept of negative 4. So I'd like you to do the first differences for each of these remaining tables of values. Okay, so take a minute to do that, and then push play and ready to go through them. Okay, so again, just take a minute here and check your answers for the first differences for y equals x squared and for these two guys down here. Now, you'll notice here when you did the first differences that unlike the first one, the first differences weren't constant. They're all kind of different. Let's take a look at the graphs of these and see what we get. So if you look at the first one, y equals 3x minus 4, where the first differences were constant, we'd expect that to be linear, and we can see from the graph there that it is. Okay, now let's try these other ones here, the ones that didn't have constant first differences. So here's y equals x squared. Okay, so it looks like a curve. Here's a third one, y equals negative x squared plus 2x plus 3, also a curve. This one seems to be opening down instead of opening up. And the last one here, so another one, again, just another curve. So all these have a specific shape here that are called parabolas, and you would have seen a lot of these in your investigation that you did before doing this lesson. So all of these are called parabolas. So you can see from the graph that these are clearly not linear, which explains why the first differences aren't the same. What I'd like us to do is go back to these first differences we just did, and now do something that we call the second differences. So the second differences, so first I'm just going to call these my first differences. The second differences are the differences of your first differences. So I have these values here for my first differences, and I'm going to take the differences of these. Okay, and that's the exact same process. So here I'm going to go minus 3 minus negative 5, which should give me 2. negative 1 minus negative 3 gives me 2. And I can keep going and do all these. So 3 minus 1 is 2, 5 minus 3 is 2. And all of a sudden you see here that all the second differences are the same. Okay, so repeat this process with the other guys and we'll see what happens. So I do my second differences here. I get negative 2, negative 2. Again, bottom number minus top number. 1 minus 3 is negative 2. Negative 1 minus 1 is negative 2. Negative 3 minus negative 1. And negative 5 minus negative 3. So again, all the second differences are the same. Continue going over here. I get 4, 4, 4. And you can sort of see the pattern here. So all these shapes that we call parabolas, or are quadratics as they're often called, if you look at the second differences, they are constant. The first differences aren't, clearly not linear, but the second differences are the same. Okay, some other things we're going to look at here, and you would have seen this in your investigation, is that there's different features to these graphs. So if you look at these equations, you'll see that some of them, like this black one right here, have two x-intercepts. Okay, we have an x-intercept there and an x-intercept there. The orange one has two x-intercepts as well. Okay, we have one there and one there at 3. The purple one right here, so I'll hide the other ones here, this one still only has one x-intercept, it just touches here at the origin. Okay, it actually is possible to have quadratics that have no x-intercepts, and I'll show you an example of one right there. So let's say I do negative x squared minus 4. So now, this new one that I just plotted here, this red one, actually has no x-intercepts whatsoever. So unlike lines which you saw last year, which always had one x-intercept, unless it was a horizontal line, which could have had none, these parabolas, these quadratics, can have 0 x-intercepts, 1 x-intercept, or 2 x-intercepts. Okay? You'll notice that with all these graphs as well, they tend to, there is a point here where, which we call a turning point. So in this black one, it's a point at the bottom here where it goes from decreasing to increasing. Similar with this blue one, there's a minimum point right here, and on this orange one, there's a maximum point up here. This point is a special name. This point right there is called the vertex. Okay, and so we'll talk more about the vertex coming up in later lessons and a little bit today as well. There's also a invisible vertical line cutting the parabola in half, which we're going to call the axis symmetry. So let's just say I hide all of these here except this orange one right here. So if you look here, I've got my vertex here at 1, 4. I've got my two x-intercepts at negative 1 and 3. Well, if I were to look at the vertical line x equals 1, the vertical line that passes right through that vertex, if you take a look, wide angle shot here of the parabola, this vertical line cuts the parabola entirely in half. Okay, so this line right here, this vertical line, is called the axis symmetry. Okay, and every quadratic, every parabola has one of those. So if I look at this guy right here, this guy would have an axis symmetry at x equals negative 4. Okay, so again, all parabolas will have one of these axis symmetries. Okay, so let's label these features now. So here's a graph of a particular quadratic. Let's label the key points right here. So we got our x-axis here in black, our y-axis here in black. Now, first thing we can find here is our x-intercepts. So this particular parabola crosses the x-axis twice, crosses it there and there. So there's two x-intercepts. So that will lead me to this label over here. Okay. The vertex is the highest point on the graph, or the lowest point if the parabola opens up. So that will be this point right here at the top. Okay. The y-intercept, just like in grade 9, it's a point where the graph or the curve crosses through the y-axis. So in this case, it happens over here. And the axis symmetry, that invisible line that cuts the parabola in half, I've drawn it on here in red, is this guy right here. Okay, so let's take a look here. Now, when you looked at your investigation, you saw there are two different forms of quadratics in there. At least there is what we call standard form, what we call factored form. We're going to focus on standard form today. So as this general form, we have ax squared plus bx plus c. So a, b, and c are just some numbers, and x and y are our variables. So what you've seen so far is that any quadratic that you've graphed is the shape of a parabola or a U-shape, and there's a vertical line of symmetry that passes through the vertex. Okay. Now when we label the axis symmetry, we label it with the x variable as well, because it is the equation of a line. Okay. Now let's take a look at how the graphs can change here. So right here I have in green y equals ax squared plus bx plus c. And what I'm going to do is I'm just going to see what happens when I change the a value. So that's a number out here. So see what happens when I make it, well, let's deal with the positive values first. As my a value gets bigger and bigger and bigger, you see the parabola gets skinnier and skinnier and skinnier. Okay, as the a value gets smaller, we see it start to get wider. And let's see what happens when we start to get into the negatives. So once we hit negatives, all of a sudden our parabola now starts opening down. And as we get more and more negative, we start to get skinnier again. So this a value right here is actually telling us whether the parabola opens up or down. So an a value that's negative tells our parabola opens down, and a value that's positive tells our parabola opens up. Okay, so just to summarize that here, the graphs will open up when a is positive and down when a is negative. So almost like a fill in the blank here with the note that you have. And as we saw on the graph, the value of a also affects how vertically stretched or narrow or compressed wide the graph is. So the larger value of a, the more stretched or more narrow the graph is. And also keep in mind here that we can't have an a value of 0. If we did, you can see what happens on here. If we have an a value of 0, we actually have a line. Okay, because that means in the equation that ax squared part is all gone. We're just left with bx plus c, which really is just the equation of a line with different values for the slope and y-intercept. So the a value can't be 0 if we're going to talk about quadratics. Okay, the other thing we saw on the first slide is all quadratic relations have constant second differences. Okay, and the other thing you'll see if we go back to our tables of values on the first slide here, our second differences were positive. So our a value is positive, here the a value is 1. Here our second differences are negative, so our a value is negative. Here our second differences are positive, the a value is positive. And since the a value determines your direction of opening, again, the sign of your second differences tells you the a value, also tells you the direction of opening. Okay, so let's keep that in mind. So if the second differences are positive, the quadratic opens up because the a value is positive, and if the second differences are negative, the quadratic opens down because, again, the a value is negative. Okay, the other thing you'll notice here, you may have noticed this pattern on the first slide, but if your x value in your table of values is going up by 1, like it was in all the ones we've done so far, the second differences are all equal to twice the a value. So here's a table of values for y equals negative 3x squared minus 8x plus 9. When you go through and you find your second differences, it's actually all equal to negative 6, while our a value was negative 3, so the second differences were twice what the a value was. If you go back to our first slide, with the tables of values you did, you'll see that here. So here we have an a value of 1. Second differences were 2. A value of negative 1. Second differences were negative 2. A value of 2. Second differences were double that. They were 4. Okay, just little things that you might notice here when you're working with quadratics. Okay. Other thing to notice here, we're talking about the y-intercepts. So back in grade 9, when you were dealing with the equations of lines, you could always find the y-intercept of any equation by setting x equal to 0. Okay, well, if you look at standard form here, ax squared plus bx plus c, well, what happens if you put x equals 0 in this equation? Well, let's do it down here. So we have a times 0 squared plus b times 0 plus c. And once you put 0 in, a lot of things simplify, right? 0 squared is 0 times a is 0, so all that's gone. B times 0 is 0, so that's all gone, so you just get y equals c. So that means the value of c in the standard form of the equation is the y-intercept. Okay, you'll be able to see that from the graph over here. So if here in this graph my c value happens to be 6, well, you can see on the graph that my y-intercept is 6. If I change the value of c, you can see the y-intercept changing with it. Okay, so a nice quick way to find the y-intercept if you have standard form. It's just going to be that c value, that constant. Okay, and last but not least, if you're talking about a quadratic relation, the degree is going to be 2. So remember your definition of degree back from grade 9 when you're dealing with equation. Let's say you have the equation y equals 2x plus 3. So that was a line back in grade 9. This would be a degree of 1. So the highest power on the variables in the equation is 1. So this had degree 1. Okay, if we look at any quadratic equation that we have, okay, y equals ax squared plus bx plus c, the highest power of x in the equation is 2. So any quadratic we see will have a degree of 2. Okay, so that's it. That's all for a quick little intro to quadratics. You've got some homework there to just look through some of the main features, and we'll pick this up in lesson 18.